Bismillahirrahmanirrahim. Hi guys, how you doing? Today we will complete the second part on chapter 5. Let's see some examples on applying Newton's second law. F equals ma. Put in your mind that F is a vector. As we said, it has magnitude, or what we call it, strength and direction. Also, the acceleration has magnitude and direction. So we can apply this on the x, y, z, the 3 dimensions. So f x equal max and fy, the force on y direction, equal may, and fz equals maz, because the force is vector quantity. Let's watch this example. Moi, Larry, and Curly push on 752 boat. Here is the mass of the boat in kilograms that floats next to the dock. This is the dock, okay? They each exert an 80.5 Newton. So we have 3 forces from Moi and Larry and Curly, parallel to the dock. What is the boat's acceleration if they all push in the same direction? This is A. So if all of them push in the same direction, you will get the summation of force, the vector sum, equals 80.5 from the first person plus 80.5 from the second and 80.5 from the third. So the total force equal 3 times 80, 240, 241.5 newtons. And you have the mass, so now you can calculate the acceleration, right? Now you can calculate the acceleration. Let's see the second part. What is the boat's acceleration if Larry and Curly push in the opposite direction of Moi? Imagine that Larry and Curly push in the opposite direction of Moi. Imagine this is the direction of Moi and this is the direction of Larry and Curly. So now you will subtract, right, to get the summation of the force. And sure, we can take the 2 forces from Moi and Larry in the opposite direction, and the from Larry and Curly in the same direction, and Moi in the opposite direction. So now the summation of force will be positive sign. And if you take the other choice, you will have negative sign, but it depends on which direction Larry and Curly or Moi push the boats. So at the beginning we picture the problem. What we have here, the force for Moi, the force for Larry, the force for Curly, each equal 80.5. The mass 750 kilogram. Right, guys? So for B, he took here on the example that Moi has positive direction. So Larry and Curly has negative, they both have negative direction. So when you subtract, the total force or the summation of force will be negative. It depends on you. It depends on the choice that you will choose. Let's for A get let's for A and B get the acceleration. And the acceleration, as you see, it is in x direction as the force applied. So at the beginning, for letter A, the summation of force over m, it gives you the acceleration. The summation of force, just add 241.5 divided by 752, and the force in Newton and the mass in kilograms. So then the unit will be Newton per kilogram, or what we call it meter per second square. It is the same. They are equivalent units. And he said here, to the right. As you see, the number to the right. So both of them push as in the picture to the right. Here in the picture, as you see in the photo, Curly and Lori push on the left side in negative direction. And moi push only on the positive direction. So the summation of force will be negative because larger forces applied to the negative direction. Let's see here, AX equal. The first one for moi in positive, second and third for Larry and Curly in negative direction. So the total force will be negative. Will be negative 80.5 over the same mass. As you see, this is the acceleration. What the negative sign means in negative direction. That's it. And we will see a lot of problems in exam view sheets. Let's go directly to the third law. Do you remember that we called the first law of inertia? When the summation of the force equals 0, an object at rest stays at rest, and a moving object with constant velocity stay moving with constant velocity as long as the net force equal what? 0. The second law, F equal ma, the mathematical equation for the second law. The third law, most of you know it with the law of action and reaction. Forces always come in pairs. Forces always come in pairs. Two forces together. That is, there are no isolated forces in the universe. Imagine that you have a wall and you apply the force on the wall. F1, 2, the wall will apply a reaction force from 2 on 1 in opposite direction. Both are equal and they are in opposite direction. So the force always be in pair and are equal in magnitude and opposite in direction. The forces in a pair act on different objects. You apply the force on the wall, you are the first object, imagine, and the wall applied a force on you. Wall is a second object. So the force in a pair act on different objects. The third law is commonly stated in an abbreviated form, and it is for every action there is an equal and opposite reaction. So F from the object 1 on object 2 exactly equal F from object 2 on object 1, but it is in opposite direction. The magnitudes are equal, but the direction is opposite. The figure below shows some examples of action and reaction pairs. As you see, the guy pushes the box to the right and the box pushes on the person to the left. Those forces are equal in magnitude, opposite in direction. As you see here, the shuttle, the earth, push or has a weight, because earth is push the shuttle downward, and also the shuttle push the earth upward. The forces are equal, but you can notice only the acceleration of the shuttle, not the earth, because they are different in mass, and we'll describe that later. The third one, as you see here, a person. This is the force from the person on the object, and there is another force from the object on the person. Note that in the three examples in the figure, the paired action and reaction force act on different objects. Earth acts on the shuttle, and the shuttle acts on the earth. As a result, the forces do not cancel. The forces do not cancel because they applied on different objects. We will go to something else, what we call it free body diagram. Free or F body, B diagram D, so we call it FBD, free body diagram. It is a drawing useful in applying Newton's law. A free body diagram is a drawing that shows all the force acting on an object. To simply a real life situation in a free body diagram, the object is often represented as a point. Imagine that you have a box here and you apply a force F on the box, F1, and another person apply F2 on the same box. So instead of drawing the box, we draw only a point, represent the object. And for the first force, just an arrow represent the direction, F1. And for the second force, another arrow represent F2. And imagine there is, here is the weight downward, so there is a force downward weight. And there is a force upward, F normal, there is a force upward, F normal. That's what we call it free body diagram. As you see here, the two astronauts try to fix the shuttle or satellite. Okay? As you see, the force is not on the same direction. One force in horizontal direction and the other force from this one in y direction or vertical direction, and from the second astronaut in x direction. This is a free physical picture. A free body diagram looks like this, okay? And just write Fx and Fy. The use of a free body diagram in the solution of a problem involving Newton's law may be summarized as follows. Once all the forces are drawn on a free body diagram, a coordinate system is chosen, and each force is resolved into components. You know that if you have a force from chapter 3, we can resolve it in x direction and y direction. So Fx and Fy. So we can resolve the vector in two components, horizontal and vertical. At this point, Newton's second law can be applied. We can apply Newton's second law to each coordinate direction separately. The following example illustrates how this procedure may be applied to a problem involving two astronauts pushing a satellite shown in the figure below. Let's go to the figure. Here he gave me F from astronaut 1 on X direction, 46 Newton. And from the first astronaut, there is no force on Y direction. For the second astronaut, he applies a force only on Y direction, and he doesn't apply force in X direction. So we can get AX here and AY here. The summation of forces here for X direction, getting the summation of the force in X direction and divided by mass, you will get AX. And the same for Y direction. So we can calculate the acceleration in X direction and Y direction. Let's calculate the acceleration in X direction. F1x plus F2x. We have from the first astronaut only a force on X direction. This is the first, here is the first astronaut. Tamam? Plus the second astronaut doesn't apply force on X direction. So the summation of the force in X direction, 46, equals MAX. If you know the mass of the satellite, you can get AX. And the same for Y direction. So you can calculate X direction and Y direction acceleration. Because the force that is the first astronaut exactly equal the force for the second astronaut, as you see, but one in X direction and the other in Y direction. So acceleration in X direction is the same as acceleration in Y direction. If you want to get the magnitude of acceleration using mathematics, the satellite acceleration in both X and Y direction using the Pythagorean theorem gives the total acceleration. Square root X square plus Y square. Here we deal with acceleration, so AX square, AY square to get the acceleration. How to get the direction of this acceleration? Using this law, theta equal inverse tan y over x, or AY over AX. The numbers that you get, use it here because the number is the same. So theta equal 45 degree, because tan 45 equal 1. We will deal with a lot of problems in exam view sheets, but let's see this problem together. Determine the acceleration. Suppose a force exerted by astronaut 1 in figure, the same figure that we studied, is increased to 58. If everything else in the system remains the same, what are the magnitude and the direction of the satellite's acceleration? Hold on. The first astronaut was pushing in X direction, only in X direction. So the acceleration on X direction will change. AX equal Fx over M. Fx here is the same force he was using. It is 46 Newton. This force increased to 58. So we use 58 Newton here over the same mass. The same mass, as he said, here is the mass of satellite, 940 kilograms. So you will get the acceleration of X in the X direction. The acceleration in Y direction is the same. Okay, guys? So how to get the acceleration? As we did before. AX squared plus AY squared, it gives UA. Now, when you calculate the new theta equal inverse tan Y direction over X direction, so 0.049 over 0.062. The new angle that we get, 38 degrees. I hope it is easy for you to calculate the acceleration for an object that affected by multiple forces. Applying Newton's laws, there are several types of force that are encountered in everyday situation. They include normal force, the force exerted by gravity, and force due stretched or compressed springs, or like rubber band also, or the spring. Spring looks like that, guys, okay? We will discuss each type of force. The first one, normal force. When an object sits on a surface, such as table top, it is subject to two forces: the downward force of gravity for this object and the upward force exerted by the table. So the downward force, we call it weight. The upward force, we call it N or Fn, the normal force. And it is exactly equal the weight, but in opposite direction. Which one you give it negative sign, it's not important. Because they are equal in magnitude, opposite in direction. The upward force, which is perpendicular to the surface, normal to the surface, at right angle to the surface, is called normal force, N or Fn. In general, the force exerted perpendicular to the surface of contact between any two objects is called the normal force. And it is exactly, for the level table, it is exactly equal the weight downward. The weight of an object is equal to the force of gravity acting on an object. This is the definition of the weight, guys. The force of gravity acting on you, acting on an object. Object of mass m in free fall has only one force acting on it. Its weight. So how to calculate the weight if an object is falling down? You know from Newton's second law, F equal ma. If the only gravity is acting on it due to the earth, so we use instead of A, G. So mg, now it is the weight. So the weight equal mass times acceleration due to the gravity, or what you memorize, 9.8 meters per second square. So the resulting acceleration has a magnitude A equal G. From Newton's second law, A equal F over M, or G equal W over M. W is the weight, or weight equal mg. Therefore, the weight of an object is equal to the mass times the acceleration due to the gravity. W equal mg, where W measured in newtons, because W is weight and weight is force. So the definition of weight is the force of gravity on an object, and it is equal, we call it sometimes Fg, we call it mg. This is what we call it weight. So there is a big difference between mass and weight. When somebody asks you about your mass, you have to say your mass in kilogram. Yani imagine that my mass is 70 kilogram. What is my weight? My weight equal my mass 70 times 9.8. If you are asking about my weight on Earth, it is approximately 700 Newton. So my weight 700 Newton, my mass 70 kilogram. This is approximately, guys. Your weight, it changes depending on the place you are in because it depends on the gravity. Gravity on Earth is different than the gravity on Moon or Mars. Weight and mass are not the same. Weight is measured in newtons. Let's see this together. Mass, weight. Mass, the amount of matter in an object. Weight is the force of gravity on an object. Mass is measured in kilogram. Weight is measured in Newton. Mass doesn't change from place to another because it is the amount of matter in you. It doesn't change. The weight changes from place to another depending on gravity. The gravity on the moon, guys, is 1/6 the gravity on Earth. So you weight less on the moon, but your mass is the same on the moon and Earth. Weight is a gravitational force. Mass is a measure of an object inertia related to inertia. Do you remember inertia? Tendency of an object to resist any change in motion, in state of motion. The mass is a measure of the amount of matter in an object. It remains the same regardless of location. The weight is dependent on the gravitational force in a given location. The gravitational force on the moon is less than the gravitational force on Earth because the mass of the moon is less than the mass of the Earth. As a result, the weight of a 81 kilogram person on Earth 795, 81 multiply 9.8 on Earth, but only 131 Newton on the moon because the gravity on the moon is less than the gravity on the Earth. This is enough for second part in this chapter. And let's go to another chapter. God save all of you guys.